back to Reading Between the Lines. Welcome, welcome. Today, we are going to be talking about electricity and the idea of free electricity. Many of you, most of my audience is familiar with the theory about Tartaria and the free electricity world, or the world of free energy that people lived in before something happened. And I've been looking into that, like the realities, the actual theory of electricity, and magnetism. And I kind of wanted to just give you guys just a real quick crash course on some of the things that I learned so that maybe you could take this as a shortcut and expand on it. And we could actually maybe figure out the secrets, right? Because it's really one thing to know that maybe there are secrets out there. And it's another thing to actually maybe be able to crack them. So this idea of free energy would be, people think that the energy was collected from the air rather than ran through wires. And I'm going to kind of go over the difference between those two and give you just a breakdown of the properties of electricity, the way we use it. And then you'll see, we'll just kind of go from there. Okay, so first of all, the way we use electricity today. We use electricity when it's conducted through a wire, right? A wire is made up of usually copper, but it's some sort of a conductive material. And it has to be a closed circuit. And this is the potential energy, right? And it's the polarity. This is a DC current. It just goes in one direction. But how does it do it? Why does it do it? Well, let's take the element copper. It is on the periodic table, it's number 29, which is important, and I'll explain why. And this is why copper is so conductive, because, see, these are all 29 of his electrons, and electrons like to pair. It's what they do, they're attracted to each other. So he's got an odd one here. The copper molecule has one odd electron hanging out on the edge. And that's what makes it so easily, electricity so easy to travel through it, because the way electricity travels through this is a good kind of like this. This is just an explanation, but pretend these are copper molecules with each one has one electron hanging out. So there's a charge introduced, and this electron is attracted to this other one because they like to be paired. But because of the energy of the exchange of electrons, the electron keeps jumping, right? There keeps jumping one, and it goes all the way through. Have you ever used one of these? Like when this hits, basically these don't move and then that one moves. It's a very good analogy of what happens when electricity or electrical current is being run through a copper molecule. It's the electrons on the outside that are sticking to each other and then causing energy, and then it just keeps going from there, and it keeps jumping and going along there. So it's not really a tangible substance. It's the charge that happens, the energy, the energy that happens as this process goes on. So let's see, this is the copper cable between these two green lines here. That's the the copper, basically the conductive element. So, or conductor or wire. As it's happening, as this process is going on, as the electrical current is moving down the line. Gosh, I keep doing that. What happens is an electromagnetic, just a magnetic field is created during this process. And it is a field that runs transverse to the flow of the electricity, which means that it's directly perpendicular, and one does not come without the other. They are always together, which makes me think that the magnetic field is kind of a mirror negative image of the positive electrons that are causing the current. I hope that kind of makes sense to you. I've been studying this for days, and it's pretty complicated. So the thing is we know that the language for this is very suspect. I think they make it on purpose, because it's not real complicated, this whole idea of it moving around into, a circle. And the reason that this filament lights up is it comes here. The filament is a really thin wire, and it causes resistance. It's like when you're using a water hose and you put a nozzle on it to make the water not be able to come out so fast or come out as much. It comes out faster and harder. It's the same idea here, and the energy causes that to glow. That's not very complicated, right? This is a little bit more complicated to understand the dynamics behind it. But when you look it up, you see all kinds of different takes on it, but they're all slightly wrong. And I just wonder, I'm like, why is that? For instance, this here says energy transformations. So the electricity comes in as energy, the electric charge. It comes here and then it comes out as heat and light, right? We know that. But what about the magnetic field? That is a byproduct of this process as well, an intrinsic one. Why isn't anybody talking about it? Because they're trying to confuse you. They really are. In fact, you need this magnetic field in order to create electricity, which they don't want you to know about that. Here's some more about how they use it's so confusing to learn about this, and I know that it's done on purpose. So look at these different definitions. This was common. I found many different definitions all over the place, which is why I chose this, because it kind of breaks it down a little bit, how many definitions there are. The scientist's definition. Electricity solely refers to the electrons and protons, in essence, the electric charge of an object. Okay, but what about the electrical current? Because to most people, that's the electricity, which is, okay, so this is just referring to the positive and negative charge of an object, but that's not what electricity is. So everyday definition, electricity is the electromagnetic field of energy transmitted by batteries and generators. Transmitted by batteries and generators? I thought the electromagnetic field happened because of the current that was happening. Transmitted by generators? But generators conduct, or they make the electricity, but they don't transmit it so much. I mean, what? It's so confusing. And then elementary school definition. Electricity is the flowing motion produced by an electric charge. Okay, the flowing motion, but I think that it's closer to say that it's actually the charge itself, wouldn't you say? It's just, they do this on purpose. Working definitions. Electricity is the amount of imbalance between quantities of electrons and protons. What? Okay, that doesn't make any sense either. The imbalance between quantities. Well, yeah, we heard about that up here, but that's kind of part of it. That's part of the mechanisms, but as a definition for it, that doesn't make any sense. So they're trying to confuse you on purpose. I totally believe that. And then do you remember a few years ago when they tried to outlaw the filament light bulb, and they tried to make everybody have the fluorescent ones or the LED ones? And it didn't make sense because it really wasn't going to save that much electricity, and it really wasn't going to save that much money. Do you ever wonder what that was about? Well, I did too, and I didn't really figure it out until today. I think what it is they wanted to outlaw the filament light bulb because they're trying to make electricity even more confusing. They're trying to be gatekeepers of this knowledge. Because look at this. This is pretty simple, right? You can even wire this up to like a potato, and you can light a light bulb, or a lemon slice, and you can light a light bulb. And it's pretty obvious that why this is lighting up, the resistance, and this is turning bright red. And that's like the easiest concept that I've explained so far. And they wanted to outlaw that. The other light bulbs that they want you to use gases, and they're not so straightforward, and it's much more confusing, and you can't really just look at it and know why it's lighting up. And I think it's because they're trying to be gatekeepers of secret magic. And in 150 years, how much will the average person know about electricity? I didn't learn hardly anything in school. I spent a lot of time on YouTube yesterday looking at videos, and most of the people teaching them had accents from India. It was difficult to find a video that I could actually understand. The reading was a little bit better, but there was a lot of it, and it contradicted each other. I think that they're trying to lock us out of this entire knowledge and only have, a certain group of people understand it, and only understand it on a fundamental, on a working level, and not really understand it. That's the biggest thing that I took from my research. It was really disturbing, actually. But that's how electricity works the way we use it, with electrical current that is kind of forced into these wires. And I'll explain a little bit more about that in a minute. The other form of electricity that perhaps the people from the Tartarian, I don't know, kingdom or whatever, what would you call that anyways? The era, I don't know. If they were collecting energy out of the air, they were collecting it from electromagnetic waves, most likely. I mean, that'd be the obvious way that they would do it. What is an electromagnetic wave? Well, it's a light wave. Although light waves can come in different forms. They start with radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays. Okay, they go from waves to rays. I don't know, that's probably just more confusion, right? So depending on the wavelength and the frequency is which one that this falls into. But these things, they're not like sound waves at all. Sound waves are actually directional, okay? These are not directional. So like a sound wave, hold on. I didn't save this picture, I apologize. So a sound wave, there we go. Come on, what's happening here? A sound wave, there we go, is directional. It only goes one way, and it's a single wavelength, right? And it's going towards you. Electromagnetic waves are weird. They actually are they're emitting this way towards this is the direction that it's going, and they're coming out this way. It's called a transverse wave, which means that the wave is happening exactly perpendicular to the direction, as well as to each other. This is a magnetic field, and this is an electric field, and they're oscillating along this axis in this direction. And a sound wave would be going just like up and down here, right? Up and down here on one plane. These are going out, okay? So I know that's confusing. It's hard to really grasp, even for me. Like, I was like, okay, I guess that's makes sense. Or I guess I can kind of think of that. This is what an electric field looks like, and this is what the magnetic field looks like. And the way that you actually create electricity is you have a conductive wire, like a coil of copper, and then which would be a potential electric field. And then you run it through these magnetic fields, and the collision of the I guess the electrons causes electricity, and then it gathers in the wire, and then it comes out the current. So it's the magnetic field causes the charge to happen, and that's how you create electricity. So isn't that just about as confusing as they could make it? Like, I'm sure there's a better way to explain all this, and it really, I don't know. I don't think they could have made it any harder to explain, and it doesn't seem like it's that crazy of a concept, right? So electromagnetic waves, which is light waves, right? Transverse waves, which I already told you, perpendicular to the direction, travels at the speed of light. Well, they're light waves. Why don't they just call them light waves? More confusion. They can travel in a vacuum, according to this. That doesn't make any sense to me at all. How can a wave travel in a vacuum? Let me explain. A wave is not tangible. It's a shape. A wave does not exist without the medium. Without the water, there's no wave. Wave is an expression of a movement. It's not an actually tangible thing. So it can't travel through a vacuum. It's impossible. Sound waves travel, and they hit the molecules in your ear, or the molecules in the air, and they just kind of bump, 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 and the energy is transferred eventually until they hit your eardrum. This doesn't make any sense. there's no way that this could travel, a wave could travel in a vacuum. That is just impossible. Completely impossible. Maybe they're explaining it weird, but whatever, it's impossible. Otherwise it wouldn't be a wave. So I don't know if you guys are familiar with the concept of the ether, which was Nikola Tesla's, or he wasn't the first one, but it was back in the 18, before they changed it. It was what the scientists thought that light waves traveled through, basically the medium that light waves traveled through. This here is a lie. All matters come from a primary substance, the luminous ether. That's not true, and he knows that. That's another deflection. That's to make you not understand the ether. That's to make you think that the ether doesn't exist because of this lumina of Ferris, which, okay, so lumina is light and Ferris is magnetic ether. But I don't know if all matter comes from this place, but lumina, Ferris, he understood at least this medium that light, that magnetic and light traveled through existed. Okay, it has to exist. And what I believe is, I think that there's something missing here, right? This looks like only half the story, but those are the two forces that we can detect, right? We can detect light because we can see it. We can detect electricity because we can see it. We can see what it does. We can detect magnetism, not with our eyes really, but if we add, sort of, because this is little iron fillings, right? We can detect it with magnetism. The fact that we can detect it means that it must exist, right? This force, but it may not be a force. It could be a medium, basically. Now, Isaac Newton famously discovered gravity, but I think it's all a crock, personally. And it wasn't an accident that he used the apple allegory with the Adam and Eve connection and the tree of knowledge, and he's sitting under the tree and it hits him, it falls off. I mean, there's just so much symbolism there. And I think it doesn't make any sense. I mean, it's not necessary. You don't need gravity to explain the laws of the universe. For instance, things like helium and hydrogen, the reason that they float, like when you put a balloon around it or anything, is because they're lighter than all of the other elements. I remember being a kid in elementary school, completely confused at why the balloons would float despite gravity. Oh, because it's lighter than air. Well, then how does gravity affect it? What does gravity have to do with anything? And the answer is nothing, absolutely nothing. Magnetism is the stickiness or the force that attracts on an atomic, an atomic, subatomic level that holds the world together, not gravity. It's magnetism. That's what holds the nucleus together in an atom. There's no need for gravity to even be a part of any of this equation. The only thing it even comes into play mathematically is when you're dealing with relativity, and it's just barely coming into play at that point. Otherwise, it's not even a force that you use when you're calculating anything, because it's not real. It's really just, it's not real. What it is designed to do is to confuse you. It's designed to confuse you and make you misunderstand the force of magnetism. Okay, now I'm not claiming that I understand it perfectly either. This is just kind of an intro to get you guys started, so maybe somebody will be interested and take it from here. But just drop all ideas of gravity, because it's designed to help make you misunderstand magnetism, period. Here's some more deliberate language mistakes, okay? So this is talking about electricity. And it says, from a scientific standpoint, what happens is that electrons in the atoms move by a magnetic field. These moving electrons provide the basis of electric power. It's that old saying, for each reaction, there's a reaction. That's not the saying. The saying is for each reaction, there's an equal and opposite reaction. Equal and. That's 2 more reactions per action, okay? So what about the opposite reaction? And that's what magnetism is. It's the equal but opposite reaction of the current transfer. This is just, I threw that in there. This is the symbol of Taurus, symbol of Taurus. Oh, which reminds me, I did the video, the other day about the veiled prophet, the Order of the Veiled Prophet, and I think that the horns on the oh, I don't have a picture of him right now. Oh, the horns on that character, you know, their mascot of the veiled prophet, they come up like this around his head. I can't believe I missed it, but obviously it's the symbol of Taurus, which is the symbol that represents the properties of magnetism. See that? That's the hole right through there that the current goes through that's creating the electromagnetic current. And so that's how you make electricity. If you ran this magnet down a long copper tube, you're going to create electricity. And then when you coil the copper up, you know, and get a huge amount of it and run it around in a magnet, then you have enough extra electricity to run a current through the wire. So they're the inverse of each other, the magnetic field and the current. Okay. Electric current is not the only kind of energy. Obviously, energy, that's not the only way to transfer energy. There's thermal energy or heat energy, nuclear energy, which I don't even understand at all. Light is energy, chemical energy, explosions, potential energy, stored energy like a battery, kinetic energy, energy that's moving, magnetic energy. Now, I don't understand this idea of magnetic energy at all, and I don't know anyone who does, and I looked up all kinds of stuff on it, and hardly anybody, they can describe it and they can describe how it's used, but nobody can really just knows what it is. Nobody can explain it on an elemental level the way that you can explain the electric current, you know, with the trading of electrons. This supposedly is induction energy. This is supposed to be magnetic energy, but I don't know. I don't know what it does. And nobody can tell you. Nobody. So I just kind of broke the word down a little bit. Induce, deduce. It's kind of like a pull and a push, maybe. You know, that's why they're the inverse of each other. The positive electrocurrent could be the electro field, and the negative current maybe it's magnetic field, and that's why they can oscillate on that wavelength, because they're pushing each other away from each other. I don't know. So I got this from that website, from that big machine. This is kind of a weird thing here. It's kind of creepy. This website, it's what do they call it? IE energy. Oh, inductive energy. And they have all these different, like, ooh, it's going to be the best thing ever. We can't, Earth engine. We can't wait to get started. But it doesn't really tell you anything about it at all. So, and it just is kind of asking you for a bunch of money. But it says it's off-grid power, game changer, but there's a patent to it, so you can't really, so nobody really knows what's going on. And the language is totally coded. They give you a description of it, and they say that it's using the slingshot effect of gravity is how they're creating electricity. And yeah, we know gravity is just not even a thing. And the slingshot effect, you know how they say that that's how the orbits happen? It's just ridiculous. And then all of this is happening in these charges, and they call them rare earth minerals. All of our cell phones now, the batteries, they're calling the elements in the batteries rare earth minerals. They just decided to ditch the periodic table altogether, completely. Do you know what a rare earth mineral is? I don't. It's not on this chart. It's not on the new ones. They just decided to throw that out because this is too explanatory. This gives you the number, tells you how many protons is in there. The other number tells you how many neutrons are in there, tells you its weight. I mean, just being on this table gives you a really big clue to the properties of whatever material you're dealing with. But they just recently, this happened just like the last 10, 15 years, they ditched it altogether and they just call it rare earth minerals. And they do that because they're gatekeepers of knowledge, right? That's the only reason that they do that, which is ridiculous. So I was trying to think about this whole idea of energy traveling through the air. So we know how it travels through a wire. We know how light travels through the air. So we know that it looks like they had light or some sort of, I almost want to say these buildings were glowing, right? It doesn't look like these were light bulbs, but it looks like it was the actual buildings that were glowing in these old pictures. Now, of course, this is doctored up and, done up to where you can see it better, but this is taken from, an old movie and kind of colorized a little bit to give you an idea, but those aren't all light bulbs, I don't believe. And if they're not light bulbs, then what's glowing? Is it the building itself? And I kind of think that that's true. I mean, you look at the moon, and this is kind of the inverse of the sun, isn't it? We know that moonlight is colder than sunlight. And it looks to me like a luminous body of its own. It doesn't look like a reflection. Rocks don't reflect light like that. I mean, they just don't. Either the properties of the rocks on the moon are completely non-absorbent to UV light or to light at all, and it's just completely reflective, which I don't think that's true. It looks almost like it's luminous all by itself. So this is the idea we already know is going to go about the electricity that goes through the wires. When you force it through the wires and it comes and we make the filaments glow, right? That's because of resistance. Resistance causes friction. That's how we get light. What causes, the question is what causes magnetic friction? If you're going to be trying to move a magnetic current or a magnetic field along, what is going to cause magnetic resistance? Or resistance or non-resistance, right? This doesn't provide much resistance at all. This is a conductor and it just flows right along. What kind of a material can a magnetic field travel right along with? Or this is volcanic, right? Basalt. It's volcanic rock. It's rich in iron and magnetite. The grains behave like little magnets, aligning with the Earth's magnetic field. As it cools, all of the molecules in basalt lined up with the magnetic fields of Earth. So when magnetism travels through these, it doesn't have much resistance because all of the molecules are lined up and it can just travel right through. This is pozzolana. I don't even know. This is the kind of cement that the aqueducts were made of and that a lot of the old buildings were made of. And a lot of, not just the buildings, but a lot of times the mortar in the buildings were made of. We know the red bricks have a lot of iron oxide, which is a conductor, and it can even store potential energy. And the mortar, we know here, has a lot of volcanic ash and ground up basalt in the cement and the mortar. The etymology of basalt is taken apart here, and it comes down to touchstone, right? Which is to test, but it's similar to lodestone, right? So, oh, sorry, this looks like the magnetos. So the aqueducts, oops, I kind of did this out of order. The aqueducts there, what I think is possible, is that these buildings and some bricks were the ones that were lighting up. That's totally what I think, and I think I can show you how that is. Now, and I also think that the aqueducts were cooling mechanisms for this energy, okay, to release the heat. Because that you hear a lot of stories about the cities in Russia and like up north, like in Sweden, in Scotland, and all these places that were really cold places, and people were living there and thriving there in ways that they don't do today, and they didn't have any their methods of heating were not that great. You know what I mean? I mean, in Ireland and Scotland, they didn't even have any trees. So when you're making electricity, this is a stator motor. This is the copper wire. This is the big magnet, and you run it through there and you spin it around and you're creating electricity. So this I just shared because look, that looks a lot like the wire, right? That you're going through, and then you have the magnetic field that goes around. What about that one though? We're missing one. We know what the wire is here. or here, but maybe there's another force that we can't see. I think that these two are basically representing the spinning around, right? Which is a lot like how we create electricity here and here and here. So, but you look at these old rose windows, right? And this is made of iron, which is very conductive. A lot of times there's lead involved. There's all kinds of different metals. I think these might have spun at one time. I really do. I think that they might have spun around. I don't know if it was the bells or the singing, excuse me, that caused it, but I think these were stators. They may not have been as powerful as a stator like this, but I think that these were enough to cause electricity to flow into the bricks of the building and to light it up, to make it glow. I think that the way they used energy was different than the way we use today. We need to make sure that, if we're looking for the secrets, we need to make sure that we're looking and asking the right questions. They obviously didn't have wires the way we have wires today. They didn't use energy the same way we did. What they were using it for was light and heat and likely transportation. Look at those red bricks there. This looks a lot like a stator, right? But the red bricks have the iron oxide. And this could be lead, it could be anything, it could be magnetized. This is the inversion. Usually we have the magnet on the outside in stators, and then this is the conductor, the coil. This could be the other way around. It could have the conductive element on the outside with the magnets on the inside spinning, creating a current. It's going to be a different kind of current than the one we're used to that is released through the conductive wire. This current is going to be probably released all the way around, right? And I think that they were conductive. This is an example of one. This is just pure iron. And if you look at it, that almost looks like a train wheel, like that would fit on a track. It almost looks like it fits right into something. Throw some bearings in there and that thing would spin all day long. Or have another magnetized track on the outside that's, different, like so that they repel each other, and that thing would spin all day long. If you had a negative on the outside and then this was positively charged, the other one was negatively charged, it would constantly spin. It would never stop. That, I think, is the secret to a lot of this. Another one, doesn't that look like it moved at one point? It looks like I just want to spin it, don't you? Look at this, is the yin yang again, and look at that. That looks like a representation of electricity, doesn't it? This is one of those magnetic coils. Look at how much that looks like that, right? And then, yeah, so we use the coils on the inside and the magnets on the outside. I think they had the magnets on the inside and the conductive material on the outside. And I think that was a major difference. I think that these things here, they had things spinning in there too, using that idea of positive and negative polarity, causing, they have them open and high because this is hot in this part of the world and it's going to produce a lot of heat, but it's also going to have the magnetic electricity come down here, kind of like the moon's luminescent light is cooler than the sun, right? Because it's the inversion of the sun. This idea is that the magnetic energy that's going through the building is going to be cooler, right? And that's also why they have these tall spires, though, because this is a hotter place, right? This likely could have had it up here spinning. And then there's these ones with the stained glass in. Now, these ones could have been both the same idea as, it has the magnetic metal, the lead. You use lead in stained glass, and lead is very conductive. and then having the electric conductor out here, you know, the opposite of what we do. But the colors could be breaking up the light waves too, especially if this is magnetic properties. And the spectrum, we know that the spectrum, the UV spectrum, you know, there's light you can see, light you can't see. Well, it's represented in colors for the stuff that we can see. So what if these, as they spun, because of their magnetism and that they were creating, and the light and the you know, the way that it separated the light, what if they were separating these wavelengths? Because if you separated them, you would just have an electrical field and then a magnetic field. You no longer have light, but you would have energy in two forms, right? That's what I think those were about. It's my theory. I don't know, guys. Tell me what you think. I don't know. Like, okay, so this is one with no wires, but I think those actually had wires. I do. I think they were edited out. But yeah, the aqueducts were designed as coolant because the water would run through here, yes, but the energy would also run through the bricks, right? And they look at how many like air holes it has. And that just, to me, that looks classic, like for a radiator. I've always thought that. It looks like a radiator because you want more sides exposed and you want air to move through, right? To cool something off. And if the energy, the conduit to the energy is the bricks and the, you know, the building, the structure itself. So it's going to be running through here. And the more energy you had conducting in your city or anywhere, the more of these you were going to need. Some of them, a lot of them were underground too, which could have had a lot to do with why Europe seemed warmer back then too. I mean, that could help crops, right? The ground's not going to freeze if you're running these underground, not only to run water, but to keep the ground from freezing in, you know, the northernmost part of the world. You could grow a lot more if this was, the energy was run through this underground to cool off. I mean, look at that. And even buildings like this, the columns, not only were they designed to glow, you know, perhaps, but to, or it could have just been the dome, you know, I don't know, but this could be a cooling apparatus. Lots of cooling apparatuses. Lots of them. And then something like this, I'm not sure if they were collecting energy out of the air, but this could be radio waves, or it could even just be cooling, you know, cooling and light, you know, it would look pretty fancy if they were glowing. And then that way you didn't have to have so many aqueducts because you had so many different sides exposed here, and it would cool, wouldn't get as hot. And then, you know, the Roman baths, the steam baths under Rome that you've heard about, the water coming in from these aqueducts is going to be hot. It's going to be warm, steamy. Look at this. These that are sticking up, those aren't chairs. Those are little pieces that are going to warm the water as part of this system that's releasing energy. This is an old bath house. And they were everywhere, all over Italy. And I'm sure other places too, these warm baths. And they weren't all spring water, you know, and what was making all these springs so warm anyways, right? Thought this was just interesting. The aqueduct, a canal or passage in a part or organ. Does that mean like an organ like music, or part of a whole, you know, part of like a circulatory system, right? Look at this. This building is in the water, cooling off. And this is where the electricity would be. So it was either like the rose windows or this, where it would spin, is my theory. So it was either in the domes or the rose windows. Those are the two ways that the electricity was produced, and it was produced with magnetism. More of this cooling fins, right? This, I think, was a way to discharge some of the extra electricity because they got too good at it. And if things were getting too hot, they needed a way to just send it out, right? Because that's what these do. Then I just found this. There's that horse, like I have a previous video where it kind of looks like they were adding horses in. That guy doesn't look real. See him? And you could actually do a Photoshop back then pretty easily. All you had to do is work with the negatives and use an X-Acto knife and cut out pieces and paste them together, kind of like the way movies are done today, that, you know, they still do stuff like that. So I was wondering if maybe that guy and that horse weren't really there in this, because there's no wires, you know, I don't know. And these towns didn't seem to actually, they didn't seem built for horse travel. I don't know, they just didn't. Then there's the Colosseum. Like, this was likely a huge conductor of some sort. I mean, there could have been things running around on the inside of that that nobody knew, or it could have just been a way to cool off a bunch of water before it went to town, right? Because it's a lot. They could have just cycled it through to cool all the water off, or, you know, or to cool all the, and take, to make it to where the water isn't too hot as well as the building's not being too hot. Anyway, that's my theory on this, guys. I don't know. It's kind of a long video, and there's a lot to it, and I'm sorry if it started off slow, but there was a lot of stuff in there that, you know, to cover. And I really think that this is a different kind of luminosity that they were using. And I think these were stators that were moving around using magnetism. And I think that we are deliberately misled about magnetism and the ether and gravity purposely, so that we don't ever figure out these secrets. So look into it for yourself. Don't let the gatekeepers win, and leave some comments below. Let me know how much you liked the video or how much you didn't like the video. Please subscribe, watch more videos, and I'm really having a good time with all of this. I really like making these videos, and I just really enjoy it, and I wanted to say thank you. Thank you guys, you're the best, and I will talk to you later.